Hello, good afternoon. This is Team 7, and we are doing mechatronic adjustable cane. Next slide, please. And this is our team. We have John Paul, Mark, David, and I, Eric. So the overview of this slide is, of course, the basic construction and features of the cane, the description, mechatronic system, the disassembly, like submodules and discussion of the system, and of course, at the ending, conclusion and summary. So our goal is to create a user-friendly electric-driven cane that automatically adjusts its length, providing convenience and support in various situations. We plan to deliver this on physical therapies and elderly homes. This modern cane technology, today's modern cane technology is underdeveloped, bulky, and inconvenient. The costs do not reflect functions or quality. Solutions include an electronically adjustable cane. The final product of our cane should have a good value between capability and cost when manufactured at scale. Versatile in its use on a per-person basis. Basic construction and features. The cane can lengthen and shorten depending on needs. Like people can use it on different heights, of course, and one of reason that we have this cane is that we can also use it when a person suddenly falls down. It can act like an electric jack that can even help lift up heavy users by just pressing a button. It's precise and have an adjustable rotation speed. The prototype structure created by PVC, piping, and other materials. Specifications. This cane that we prototype with is a 2-pound cane. It is adjustable. It has a 20 seconds of extension and retraction time. The maximum length can go up to 43 inches, and the minimum length can go to 30 inches. The voltage supply is 18 volts. So like what we said is that the main description of the cane is to extend and retract based on the needs of the user. The stepper motor is used and is powered using a variety of buttons to ultimately extend or retract the cane using a lead screw, a nut, and other mechanical features.
Here's a block diagram of our cane. You can see that the input is the buttons because that'll tell you if you want it to extend or retract. That goes to the microcontroller, which will send a signal to the stepper motor driver, and that will the driver will take in external power and use it to activate the stepper motor, and the stepper motor will spin the lead screw and therefore extend or retract.
Here's a video of the assembly of the device. It's pretty brief and doesn't include each and every part of the process, but in general tends to be a good summary of what the building procedure looked like. And now to resume our slideshow. So next we'll discuss the mechatronic systems and components.
The primary body of the cane is made out of PVC pipe of varying diameters. The mechanism that allows us to have linear motion is the lead screw. Here are the specifications for it. Attached to the lead screw is a T8 nut. And the actual actuator is a stepper motor to supply torque. And the coupler here was used to connect the stepper motor to the lead screw. And here's an adapter bit. We had a few. This is to make sure that the stepper motor shaft fits into the coupler that came with the lead screw, and these were 3D printed.
Here we have an image of the circuit that makes the cane function. The main components are microcontroller, buttons, the DRV 8825 stepper motor driver, and 9-volt batteries. So here's just a quick summary of how the DRV stepper motor driver works. In the top right, we have the VMOT, which is the power supply that powers the stepper motor, and we used 18 volts. Then comes a ground, and then comes the coils from the stepper motor that make it step. A fault is just an output that doesn't really do too much to drive the stepper motor. And we have a ground. The step and direction pins are connected to the Arduino, and that's how we control the direction and the step size what the stepper motor rotates at. Sleep and reset are active low pins, so we had to supply them with 5 volts to ensure that the driver was working. Above those, we have the M0, M1, and M2, and these are how you control the step size by either making them high or low. And the enable was left as low just to make sure the driver was functioning properly. Here you just have a quick snippet of our software. It's pretty simple because it's open loop control. But the way it works essentially is we make the direction steps outputs. And if the direction is either high or low, each value corresponds to whether it's rotating clockwise or counterclockwise. The steps, the motor completes a step with every pulse. So we had to, with Arduino, create those pulses. And you can see that in the loop function, we have 2 if statements, basically saying if one button was pushed, it would rotate clockwise and then go through the steps, or vice versa. If the other button was pushed, it would rotate the other direction. And the speed can be controlled with a delay of the pulses. So the shorter the delay, the quicker the pulses happen, meaning more steps happen frequently.
So now we'll discuss our conclusion and summary. So in regard to problems and learnings, one of the main issues was our difficulty collecting adequate materials in a timely manner. Typically, the components that we would order on Amazon. So anytime that we ran into an issue, realized we forgot something, or in general, something just didn't work, we had to wait a couple days for the new product to ship. We also learned that 3D printed parts are quite valuable, and that essentially how do we use them from the beginning? We could have completely customized every single part of our device instead of trying to make things do with PVC pipe. Next, we learned about the requirements of different motors and their drivers. We also learned about the mislabeling of Amazon parts. A lot of the product descriptions are accurate, especially on those cheaper items. And we did find that precise drivers proved to be pretty much the most challenging component used in the project. Moving on, we try to use a rack and pinion for our motion. We also try to use bevel gears and DC motors of varying output RPMs. And we found that the rack and pinion would not really be ideal for packaging. Bevel gears introduced unnecessary complications and moving parts that we didn't need to have. And DC motors couldn't really be modified well enough to meet our design requirements. So anytime that we wanted to make a change, we needed to order a new DC motor, which is not effective. We had difficulties making progress early on, but as we gained a little bit of experience and more parts to play with, then things sped up and we were able to create a prototype relatively quickly. So To conclude, the device is used for biomedical applications and provides variable support depending on the user and the need. Future iterations will certainly include more 3D printed parts. We'll also need a custom PCB because as it stands, it's quite difficult to fit a microcontroller and the batteries and all of the other components within any reasonable environment. They kind of just hang out on the side, as you guys saw during our build video or our overview in the beginning. And we'll definitely want to use stronger materials to support more weight and to make the lifespan of the product longer. So thank you. And now I'll just show a quick video of the device functioning and what our final prototype looked like. So this video here is pretty much just a quick snippet of the device retracting. And so for now, that will be all. That is our product, and I hope that you liked it. Thank you for watching.